We are still going to study branching random walks, but the model will be slightly more complicated than standard branching random walks we have studied so far. We add something which we call selection. Why selection? So I guess many of you know the origin of the study of branching processes. So branching processes the study was initiated by Watson and Galton. So initially they wanted to know the chance of survival in the big families in Great Britain. And we also know the conclusion is that for the branching process, there is positive probability of survival if the mean number of children is strictly greater than 1, and otherwise, if the mean number is smaller than or equal to 1, then we know for sure that sooner or later there will not be anybody. The process will die forever. Okay. So that's the conclusion for the standard Galton-Watson process. There is something which is peculiar, a little bit surprising in the conclusion is when it survives. So if you assume that the mean number of children is strictly greater than 1, so the conclusion is that with positive probability, the system is going to survive. And it's part of the conclusion is that the number of individuals in the system is very, very big. It goes to infinity exponentially. And that's not very realistic with the real life. And Watson observed that as well. If a big family did survive, the number of persons in the family was not exponential. Well, luckily, because we live in the compact space. So if the number of individuals is exponentially large, then we would have big troubles. So it means that the Galton-Watson branching process is not very realistic. Something is missing in this model. And from biology point of view is, if you believe in Darwin's evolution theory, what's missing is a criterion of selection. So that's somehow the original motivation to introduce a selection criterion in the branching process. So in our setting, when we study branching random walks, so we have the value of the branching random walk. Mentally, it represents something bad, meaning that we want to have the values of branching random walk as small as possible. That's why we studied the minimum value and so on and so on. And here again, we are only interested in the individuals where the value of V is very small. So there are several, in the literature, there are several choices for selection. So let me start with, I'm going to introduce 3 very simple selection criteria. So the first one is so-called absorption. So let me start with the usual notation of branching random walks. So usually we call V, capital T is the genealogy of the system. Okay, so here for me, X is an individual, yes? it's a vertex in the genealogy tree. So V of X is the value of this individual in the system branching random walk, and mentally for me, it's something bad. So I'll call it a defect of the individual X. It means that the larger the value of V of X is, the less interesting the individual is for me. Okay, so somehow I'm more interested in the individuals in the system where the value V of X is as small as possible. So that's the basic idea. Okay, so we always assume the assumption star. So I will write it here. I'm not going to use the exact equations of the assumption today. We are going to see that there is absolutely no technical computation today. So there are two identities for the assumption. So I always assume that we are under assumption star. So let me remind you that under the assumption star, if I look at the minimum position in the nth generation, we know that it's sublinear. Divided by n, it goes to 0 almost surely. Well, almost surely on the set of the survival. And moreover, it goes to infinity. Well, actually, we know a lot more than that. Because last week, actually, we spent an hour and a half to prove that actually it goes to infinity, like, roughly speaking, like 3/2 times log n. That's what we proved last week, right? Okay, so now I want to introduce a selection criterion in this model. Let me make a picture. So this is the position of the branch random walk, and this is generation. So according to definition, originally I only have one particle at 0, and at first generation, let's say there are 2 children, and then let's say this one has 3 children, and this one, let's say, has 2. And then let's say this one has only 1, this has 2, this has none, let's say, this has 2, and this also has 2, and so on. Okay, so this is a typical graph for branch random walk, and I know that the minimum value goes to infinity. It means that sooner or later everybody will go very, very high, but sublinearly, we know that the lowest position is, roughly speaking, 3/2 of log n. Okay, so now not everybody is going to be selected in my new system. So this was the original system of the branch random walk. So now I say that I don't want to keep everybody in my system. I want to select the best ones. What are the best ones I mean? By best ones, I mean that these are the ones with very low value of V. I don't want to have these high values. Yes? So concretely, what I'm going to do is to put a barrier, a red one. Then I say I kill everybody whenever it goes above this wall. So this wall is killing. I remove everybody whenever it goes above this wall, then I kill him. So I only keep those who are below. So now let's see. In the first generation, in the original branch random walk, there were 2 particles, this one and that one. but the first one is already above the wall. So this one actually is not selected. It gets deleted immediately. If someone gets deleted, I mean, he doesn't have time to produce children, grandchildren. So this one, not only he dies, but we are not going to see any of his children. So this guy, we will never see it in the new system. So maybe I'll just put the ones which are in the new system. This one is good because it's below. The next one, this child is not good because it's above. Whereas this one is good, it's still below. Yes? And in the next one, this one is not good, whereas this one is good. And that's all I have for the moment. Okay, I should put some more because then this one is good. So in the new system, there are only, well, in the in the first 3 generations, there are only these 4 individuals. Everybody else gets killed because most of them come from this guy, but this guy doesn't show up in the new system. So all these guys actually, we will never see them in the new system. So that's my idea. So I put an absorbing barrier of some slope. Well, I call epsilon. So we are mathematicians. Everybody guesses that epsilon will be something positive, but very slow. Okay. For the moment, epsilon can be even negative or can be very, very big. Yes. And so each particles gets deleted if positioned above the slope, the barrier. Okay. I hope so. This will be my new model. I will call it a system of branching random walk with an absorbing barrier. I hope the definition of the model is absolutely clear, right? Okay. So for the moment, epsilon is just a real number, and I'll give it a name, rho of epsilon. I'm interested in the so-called survival probability. It means that for this red system with selection, with this absorbing barrier, I want to know what the probability is that the system will always have some individuals in it. So that's what I call survival probability. And that was my question. Okay. So the basic question is whether the survival probability is 0 or is strictly positive. And it's very easy to guess the answer because we know the behavior of the minimum value in branching random walk without selection. We know that the minimum has asymptotic speed 0. Yes? So I think everybody guesses that epsilon equal to 0 is critical. If epsilon is strictly positive, then there will be someone below because we know that originally there will be always someone at position 3/2 log n. Whereas if epsilon is 0, then probably there will be none. That's even a proof, right? Okay, the previous one, the one which is not totally immediate is when epsilon is positive. We know that there is someone at 3/2 times log n. But we also know that in this whole history, in the middle, he was rather at position square root of n. We saw that last week, even though we didn't prove it. So it means that in the middle, he was already killed. Well, square root, no, that's not true. So I don't say anything. So anyway, one part is immediate, and the other part is not proved, but I think it's very easy to convince yourself that epsilon equal to 0 is the critical situation. So there was a paper by 4 co-authors. So Begins, Lubachevsky, Schwartz, and Weiss. (1991). So their main theorem say that epsilon equal to 0 is the critical value. So they prove that the survival probability is strictly positive if epsilon is strictly positive, and it is 0 otherwise. Okay. There is monotonicity. So if it's 0 for epsilon equal to 0, certainly it's also 0 if epsilon is negative. Right? So there is absolutely no surprise in the statements of the theorem. And a few years later, so Pimentel in 2009, so if the survival probability is 0, certainly you don't need to say anything. You know that sooner or later there will be nobody in the system. In the first part, when epsilon is strictly positive, I know that the survival probability is strictly positive. But everybody would believe that if I let epsilon go to 0, then very likely the survival probability will go to 0. So as a mathematician, certainly it's an automatic question is how fast or how slow it goes to 0. And there was a conjecture by Pimentel. Pimentel believes that it goes to 0 very rapidly. It's sub-exponential. So k would be a constant. So Pimentel was interested in this problem when he studied an algorithm in computer science called binary search tree. By the way, one of the main motivations of the studying of branching random walk is study in computer science. So there were all kinds of works on searching on searching trees. And the answer is yes. So the conjecture is correct. And moreover, it's even possible to have the exact value of the constant k. So this will be the fifth theorem. So if we, under the assumption star, which I have removed already the statement because I don't really need the exact statement. So under the assumption, the survival probability is sub-exponential, and moreover, that you have a very nice constant. Sigma, we already have seen the value of sigma. Well, the value of sigma square is the variance of the associated random walk. So where sigma squared is the expected value of the sum over everybody in the first generation of branching random walk to the square e to the minus branching random walk. And according to this integrability condition, which I don't give the exact statement, it's finite. So there is a constant depending on the law of the branching random walk only via this quantity, via the standard deviation of the associated random walk. Okay. I hope this looks like a very nice result, right? I'll just say. Sorry? Oh, okay. I think it's by Nina Gantet, Yuan Hu, and myself. I think 2011, I think so. I'm not sure about the year. I'll just say one word about the proof. And I hope at this time everybody gets used. Although the proof itself requires quite some work, but the idea is very simple. The idea is I told you that I only knew one tool that was the many-to-one formula, and this is a typical application of the many-to-one formula. So proof by the many-to-one formula. So I just recall the many-to-one formula in case you forget it. So I take whatever n, I fix a generation n, and I sum over everybody in the nth generation. I take whatever measurable, let's say non-negative measurable function of the branching random walk. And actually, I can take a function, measurable function, not only of the branching random walk, but all the history from the beginning until n. So v of x1, v of x2, until v of xn. xn is x itself. So xi, it's the same notation as before. xi is the ancestor of x in the ith generation, right? Okay, there's nothing very special. So I take the expectation of some of an arbitrary measurable function, let's say non-negative, of my branching random walk, but a function of the whole history of the branching random walk. Okay, the only thing which is not very nice is that I'm not able to say just about one branch. I need to sum over all the branches leading to the nth generation, not just an individual one. That's the only thing which is not very nice. And it turns out that it's exactly the exact value of the same measurable function of a random walk, S1, S2 until Sn, but I need to pay some price, and the price I pay is there is a density, and the density is exponential to the terminal value of the random walk. Okay. So on the left-hand side, I have sum over an exponential number of terms. On the right-hand side, I only have just one piece of random walk. That's the essential of many-to-one. That's why you call it many-to-one, because you have many branches, and here you just only have one branch. Yes? And okay, under the assumption star, the new random walk S is mean 0, and the variance is what's stated in the theorem. Okay. So that's what the many-to-one formula, and it's probably, for me, it's the most important and very simple formula in the study of branching random walk. So how do I use this general tool to prove a result like that? So I think you can more or less guess what you are going to apply. Whoops. So in principle, a priori, the formula is valid for all non-negative measurable function g. So I'm going to take the function g, the indicator function, such that everybody is below the slope, let's say. Yes? So, which means that ui is smaller than epsilon times I for all I. That's in principle what I want to use. So if this sum is 0, it means that there is nobody satisfying that. It means that everybody has been more or less killed before reaching the nth generation. And exactly as in the proof for the minimum position leading to this 3/2 log n story, it turns out that, so there is an upper bound and a lower bound for this. So upper bound is saying that the probability is smaller than this one, and lower bound saying that the probability is bigger than this one. Yes? And one of the bounds is, the upper bound is a story of the first moment, and the lower bound is a story of second moment. Unfortunately, the second moment, just as for the minimum position, actually taking this is too big. So you need to put some additional things so that you don't lose very much, but the second moment will become smaller. And that was the story. It's exactly the same idea of the proof for the minimal position. Okay, I don't think I want to say more about that, but you see the idea. So the main step is the -1 formula. Okay. So that was the first example of selection. Now I want to say briefly another example of selection. This branching random walk, and this time the selection is not you kill someone when it's above a slope, but rather there is a competition between each other in the system, and this resulting system has a name. Usually we call it capital N branch random walk. So for the branching Brownian motion, so let me start with branching Brownian motion. So I'm going to tell some motivations. If I look at U as a function of the pair time and space, okay, this x has nothing to do with the vertex x in the genealogy tree, has nothing to do. X here is just a real number. I look at the maximum position of branching Brownian motion at time t. So as a function of time t and space x, it satisfies the so-called FKPP equation. We briefly saw this at the very beginning, so here is a reminder. Except that at that time, in the first lecture, it was the distribution function, so the inequality was in the opposite way. So that's why in the first lecture here, there was a negative power, there is a negative sign. You just replace everywhere u by -2u, so it means that here you have a minus sign before. So let me remind you that, be careful, it's the tail distribution, not the distribution function itself. And of course, the initial condition is the indicate function that x is negative. And there was a very visual representation of the function u, the so-called traveling wave solution of the FKPP equation. So at the beginning, there was nothing special, so that's the indicator function of the negative parts. And then, so that's it. Yeah? So that's u of 0x, if I take this x. So at the beginning, the negative part is positive, and then it's 0. As soon as t is strictly positive, immediately everything is strictly between 0 and 1. That's something is strictly greater than 1. And oops, I think I prefer to, it will be very, very large. And oops, when t goes to infinity, okay, it moves. So if you look at, let's say, medium or whatever quantile, if you look at 10%, so it's something like there, let's say. So here I take, let's say, the medium. Then actually this one, when t is large, you always see the same picture. But it's as if you sit here, then you don't see much difference. You get the impression that you always see the same landscape, the same scenery. Yes. So there is. That's why we call it traveling wave. It's kind of wave, the same thing, but it does move ahead with some speed, and the speed is square root of 2. So I take this one, but I could have taken the quantile points of 10%. You have exactly the same story. So that's the traveling wave solution for the FKPP. And the physicists had a lot of different of extensions of the traveling wave stories for FKPP. And we are going to see that there are at least 2 very simple perturbations of the FKPP equations, such that you don't exactly look at the FKPP, but you give some very small perturbations to the equation. You still see some similar story, that you still see traveling wave solutions, except that the speed, the asymptotic speed, will not be exactly square root of 2, but something which is very close to square root of 2, but which is not exactly because of the perturbations. We are going to see that after the break. So let's take a break of 10 minutes. Okay, so before the break, so we record the FKPP equation, and we saw that there was a traveling wave solution with asymptotic speed exactly square root of 2. Asymptotic meaning that you look at this position, you divide it by t. When t goes to infinity, it converges to square root of t. Okay, so it's possible to add some small perturbation to the FKPP equation. So here I will just use 2 examples of small perturbations. The first one is with cutoff. So this was introduced by Brunet and Derrida. They are all physicists. I told you that there was a huge literature in physics about FKPP. So more or less, these 2 teams more or less studied this at the same time. So the first team is Brunet and Derrida. The second team is Kessler, Nair, and Sander. The work were done, I think, more or less simultaneously and independently. So you take the FKPP and you add a cutoff, meaning that this additional term to the heat equation, you only care when u is not 0. It's greater than epsilon. Well, it turns out that I prefer, instead of epsilon, I prefer to write 1 over capital N. So at the end, my capital N will be very, very big. So this plays the role of epsilon. The notation is very unfortunate because we have a symbol capital N to denote the number of particles, number of children for everyone. It has nothing to do with it. Okay. Capital N is, for the moment, is just a fixed integer, yes? And they observed that there was something similar. There was, for this FKPP with a cutoff, when this capital N is big, then you have, again, this traveling wave solution, except that the speed will be different. The speed, okay, I will call it cutoff. It depends on N. When N is large, the speed is slightly slower. Somehow this cutoff slows down the movement of the traveling wave, but the correction is a positive constant over log n to the square when n is large. So that was one. Oops, sorry. That was one example of perturbation. Another one is more probabilistic. It's called, you add a noise, so it's called the noise FKPP.
Excuse me.
Yes?
May I ask about this particular perturbation?
Yes.
So does there exist such a, so if n is small, yes, might it happen that the speed becomes equal to 0?
Oh, I don't think there is, I'm not aware of anything when n is just 5 or 4. Okay. Then I don't know. Apparently they only care, well, they only care about the asymptotics. Yeah, so when n is 4, 5, then I'm not able to say anything. Certainly this doesn't make sense at all, yes. So the noise version is again by the team of Dehida, Brunet Dehida. I think that one was a little bit later. So this time you add probabilistic noise. Oops. So u1 minus u. Again, in principle, it's just epsilon, but I prefer to write 1 over square root of capital N, and you add w dot. So w dot here, it's the standard space-time white noise. Okay, whatever the exact meaning of this equation is, because this is cheating, I mean, it's not the rigorous definition of the solution. So whatever the meaning of this noise, well, I don't know. Excuse me. I don't write noise. Whatever the meaning of this noisy FKPP equation is, they also observe that there is also a similar traveling wave phenomenon. And again, just as in the previous example of perturbation, it's a little bit slower than the usual speed for capital N very large. And again, the slowdown is about a constant of log n to the square. And this part, the second part actually is proved. Okay, I'll write it here. This second part is mathematically proved by the team of Müller, Mitnick, which probably you know very well, and Costel. They wrote 2 papers. And in very even a very general context, meaning that you can take more general functions of that. And they were so proud of the results. I think the second paper was published in Inventionist.
This result means that somehow there is a big difference between this cutoff and noisy, in the sense that for cutoff you see immediately that when n tends to infinity, you approach your initial FKP.
Yes.
But in the second model it is not obvious at all. So
well, the second one is a formal one because it doesn't make sense as there is no derivative. You should write it in the integral.
What I can only guess that the quadratic variation plays a role.
Yes. But if you formally take capital N to go to infinity, this one will disappear. Okay.
Well, we all understand that W dot doesn't make sense. If you divide it by the process by square root of n, the thing that goes to some.
No, here there is the square root of capital N appears only here. There is no other place. So formally, if you take capital N, go to infinity, and formally, the intensity of the noise will become 0. So formally, there will be no
No at all. But this.
Yes.
Oh, yeah. I see.
Sorry.
I see. Sorry, I didn't remark this.
So formally.
Main term.
Yeah.
Okay. So I thought this noise somehow reproduces the main term, but it is present.
Okay, so these were the motivations to study what's called branching random walk with selection. So now let's back to the branching random walk. So far it's FKPP. So now let's come back to the study of branching random walk. So the team of Bohine, Derrida, and with two of former students of Derrida, that's Müller and Meunier. This Müller has nothing to do with the previous one. Okay, this one was the expert of SPD, whereas this one is physicist. Okay, so they wrote a series of 3 papers in 2006 and 2007, where they introduced the following model of branching random walk with the computation. So initially, you look at the branching random walk. Just as for the previous model with the branching random walk with an absorbing barrier. So you start with a usual branching random walk, and then now you introduce some selection criteria. So at each generation, Previously, you need to have a small value of V in order to stay in the system. Now, this time, the goal is slightly different. You don't necessarily need to have a very small value, but all you want is to beat your neighbors. So if your neighbors are not very good, then you can allow yourself to be not that good, but as long as you are still in the best ones, you survive. So at each generation, I select only if there are more than capital N particles. So N is fixed, and let's say 3, yes? Only the 3 particles with the lowest value remain in the system. Everybody else gets deleted. So let's say you fix capital N to be 3. So at each generation, you only keep the 3 particles with the lowest value of V. So everybody else, they get deleted. And of course, you don't see their children either. And that's it. So in the previous one, you need to have a relatively small value of V. If it's above the wall, then you get deleted, right? This time, your value might be relatively high, but as long as others in the same generation are not as good as you, then you are still are alive. Yes. So the spirit is a little bit different. It's really like a competition because you compete against your comrades. You need to do better than most of your comrades. You need to be in the top capital N, actually, in some sense. Okay, so that's the second model, and the resulting system has a name. Usually we call it N branch random walk for short. So we get so-called. So I will note Vn of x. The generic, I will call it capital Tn because everything depends on n, of course. So now I have a finite system because there are at most capital N particles in my system at each generation. If there are more, then I take the capital N best ones. Yes. So now I have a finite system. Then oops. In the finite system, it doesn't matter whether I take the minimum value or the maximum value, it's the same. The difference is not very big. Anyway, I divide by n, certainly, I mean, you don't see any difference. So you take the minimum, you take the maximum. It doesn't see any. So it turns out that, well, the proof of this is quite easy. Turns out that it has a constant limit, which I call V, but it depends on capital N, certainly. Almost sure. This is very easy to prove because of an argument of, I don't remember whether it's subadditivity or superadditivity is one of the sense. Because there are all kinds of monotonicity in this new model in the sense that this, I don't say anything because I know that one chance in two I got it wrong. There is a monotonicity in terms on capital N, but not the usual monotonicity. The monotonicity is in the stochastic sense. I mean, omega by omega, it's wrong. Okay. Anyway, so that allows you to have a subadditivity or a superadditivity property, so that you realize that the limit of this guy exists, which is, I don't remember either the maximum or the minimum of this one. And it's anyway, so the question is how it behaves V capital N when capital N go to infinity. And there is a very nice conjecture by Derrida and his co-authors. So that's conjecture. Well, it's a prediction, actually. So that's by Derrida, Brunet, Derrida, Müller, and Meunier. So they repeat several times in their paper. So under the standard assumption star plus some additional integrability conditions, they believe that Vn is pi square sigma square over 2 times log n to the square. And they even have a prediction for the remainder. 1 minus 6 plus O of 1 log capital N over log capital N. when capital N go to infinity. And they have all kinds of conjectures. Well, these are results from physics point of view, but the arguments are not mathematically rigorous. So from mathematical point of view, you cannot call them theorems. Okay, I want to say one word about this remainder. Well, it's not because I like to study terms like log n over log n, right? But I think what's important in this remainder is that it's universal. It doesn't depend on anything. I mean, the main term itself depends on the distribution of the branch random walk because of the sigma square. Sigma square is exactly the same variance of the associated random walk. So you see, the main term does depend on the law of the branch random walk, at least via the variance. But the remainder, the team believes that it's totally universal. It doesn't depend on anything. So I think that's probably, I mean, the exact form maybe is not very important, but the conjecture universality, I find it important. Well, that's my point of view. Anyway, so that's, and they have many other conjectures. Unfortunately, none of these conjectures is proved so far. So including one about the genealogy. So they believe that after some convenient normalization, it should converge to the so-called Bolthausen-Sneedman coalescence, which is a very nice probability subject. So far, all these conjectures are open, but there is a mathematical result, which I find it very, very nice, and which is so far the only one which is mathematically rigorous. And that was proved a few years ago by a couple of young mathematicians. So that's, I'll call it a theorem. Behar and Guehe. So I believe that to prove this conjecture, you need to have very young, talented mathematicians with very fresh ideas. And here is a very good example. So they prove that, okay, under assumption star, the main term is correct. So they didn't have this additional term, but they do prove the main term. And so far, this is the only rigorous result available from mathematical point of view. If you check the proof, they also have a second order, which is of this one, but they only have a constant between two constants, and moreover, even the sign of the constant is not clear at this stage. Yes. Okay. So that was more or less I wanted to say. Okay. There are strong evidences about the correctness of these conjectures. So strong evidence that the conjectures are correct, but it's still not proof. There is a paper by Behestiki. These are brothers. There is even their father who studied PDE. And Schwansberg, 2013, I believe. They prove that this and also the other conjecture about the genealogy, they prove that it's correct, but only for a model which is not exactly the n branch random walk, which is a model which is very close, but not exactly. So the conjectures are still open, strictly speaking. But I think this paper by basically Schwarzbeck is sufficiently convincing to convince you that the predictions by the Derrida team are correct. Yes?
Before you erase,
yeah.
I still wait whether you are going to connect two subjects you discussed.
I have
FKPP with a disturbing term of parameter n.
Yes.
Here you consider the branching random walk with competition where there is this parameter n.
Yes.
Are there any connections between the two?
No rigorous connections. It's believed that all the three ones should be more or less have similar behaviors, but you cannot jump from one to the other. Well, there is a rigorous connection between this noisy FKPP and a certain stochastic model, but not the n branch random walk, unfortunately. Oh, by the way, so there will be a conference in June, in the week of Monday, June 5th, and Derrida is going to talk about this, I believe. So certainly we can expect to learn a lot more from his lectures than here. I mean, here I tell you about all the basic things, and certainly you are going to see a lot more from Derrida's lectures. One last word about the results. You probably see that this is the square of when the survival probability, it was minus this 1 pi sigma over square root of 2 epsilon. You probably realize that these are the same constant. That's the square of this one, and epsilon plays the role of 1 over square of log square. That's because the proof of this use is that Behar and Guehe use a very, very imaginative coupling argument, saying that the problem of n branching random walk is somehow related to the model with absorbing wall. But unfortunately, I don't need to. It's impossible to explain in more details than that, because the coupling is a little bit complicated, and even I myself have troubles each time to understand this properly. Okay, so maybe I want to say a few words to finish this chapter. So that will be the last part of this chapter. There is another model of branch random walk with selection, which is called L branch random walk. So it looks like a little bit like the n branch random walk, except that here L is a positive real number. It's not an integer necessary. And that was introduced by one of the 4 course papers by Brunet, Derrida, Müller, and Meunier. So I think that's one of the 2 papers in 2006. So they introduced this L branch random walk model. Again, you start with the usual branch random walk, V. Now you introduce a selection, a criterion. So at each generation, you make a selection. In the n branch random walk, you select the n best ones. Yes, you remove everyone else if there are more than capital N. You select the n ones, best ones. I mean, with the slowest, with the smallest value of V. Here it's slightly different. It's still a competition. You want to beat your comrades, most of your comrades. Except that here, when I say you beat, it means that, well, you stay in the system if you are not beaten. And you are beaten if someone is better than you by this quantity L. When I say better than you by quantity L, it means that his value is smaller than yours minus L. That's it. Okay, so let me see. So each individual gets deleted if so you are removed from the system if you are greater than someone by at least capital L. So of course, I mean, our model is a little bit strange in the sense we want to have small values of v, right? Imagine if you want to have bigger values. It's like when you run a, let's say, 10,000 meters. It means that you made 25 rounds around the state, right? And if someone just goes beyond you just by one round, then you are eliminated, because you are too far behind behind of someone by at least 400 meters. And it's exactly the same story, except that we want small values of v, not the big values of v, right? In the n branching random walk, you want to be in the best group of 10, the first 10. Everyone else gets removed. So once you are on the 11th position in the group in the middle of the competition, then someone comes to tell you that you get deleted because you are behind the first 10. In the new model, it's if someone is ahead of you by at least 400 meters, then you get eliminated. Yes? So these are two different competitions, but certainly they are more or less related. So the resulting system, okay, I think I'm finishing. The result system is called an L branching random walk. I'll give it a name, let's say L, VL, which in knowledge I'll call it capital T of L. Okay. So like the previous model, I'll look at the asymptotic speeds. Here again, the minimum or the maximum, it doesn't make any difference at all. Here it's even easier because I know that the group is very compact. The distance within everybody is less than 400 meters. So if you divide by small n, so certainly you don't see any difference. So here you don't even make any proof, except that the existence of the limit, now I don't think it's totally trivial. I don't even know whether it's automatically true. So I define the speed if it exists.
So you cannot prove it.
I cannot.
But you have examples when it exists.
Yes, I do have a result. Well, not mine, but I do have a result. So actually, for branching random walk, actually I don't have any clever results. So assuming that it exists, I want to know what happens about the speed when capital L go to infinity. So the four co-authors, Brunet, Derrida, Muller, and Meunier, they claim that the L branching random walk is more or less like n branching random walk if L is a constant multiple of log capital N. So L is, I cannot remember which constant it is. log n. So they believe that these are more or less equivalent. Okay, but there is one result which I want to write, and that will be my last result. And I'm already, oops, I'll write the result here. The results is, I think it was last year. The results is for, not for branching random walk, but for branching Brownian motion. For branching Brownian motion, of course, you can do some exact computations. And for any L, this does exist. And moreover, it is deterministic. It's not random. Okay, well, that's not a big surprise. I guess everybody believes that. And moreover, asymptotically, Pan was able to prove that without selection, it's minus square root of 2. We are looking at the minimum, right? The maximum is square root of 2. Here we are looking at the minimum. Branching Brownian motion is symmetric. Yeah? So if formally capital L is infinity, then you get simply minus square root of 2. So the correction is, let me see.
When you say V of L exists, it means that it exists and finite. It exists and is finite.
Yeah. Well, actually.
And non-zero.
Sorry?
And non-zero.
I don't know. It could be 0 for some values of L. I don't say anything. I don't say anything. It could be 0, I guess. Pi square of 2 square root of 2 capital L square. So you see, it does confirm what was predicted by the team of the 4 physicists. So formally, if you replace L by a constant multiple log n, then you get something similar. Well, this is, the linear term doesn't count because for branching random walk, we did exactly so that there was no linear term, right? The main reason for which the result by Pan was not able to be extended to branching random walk is that in his proof he uses some very, very accurate estimates for branching Brownian motion obtained by Behestigi-Schwarzberg, and there were no non-analogs for branching random walks. That's more or less the same situation as Bramson's theorem, known for branching Brownian motion for almost, I think, for 30 years, and everybody believed that it should be true for branching random walk, but nobody was able to prove it until Elie Eidekon did that a few years ago. And here I get this impression that there was something similar, which was proved for rigorously for branching Brownian motion, but not for branching random walk. Okay, thank you very much.
Just a question. When you work with the branching random walk, then you impose normalization star condition star.
Yeah.
And when you work with Brownian motion, it is already normalized.
Not exactly. So you see there is this linear term.
Okay,
so if you want to be exactly in the same star, then it means that, let me see, the Brownian...
Is an analog of, any analog of many to one formula?
Yeah. Actually, there are even 2 analog of...
Then what is the analog of this single random walk? Is it a continuous time process, probably?
Yeah.
So
everything is continuous.
Motion?
Yes.
So you can reduce it to usual Brownian motion.
And in that time, yes, you don't. The proof is even trivial. So okay, the statement is that for branching Brownian motion, if you want to put yourself in exactly in the same setting as condition star, it means that each Brownian motion has a positive drift. Because you see, on the star, the minimum go to infinite. So sooner or later, everybody go to infinite. It means that individually, everybody has a positive drift. And this drift, I believe, is square root of 2. I'm not, yes. Everybody has a positive drift, yes? But the minimum will give you something log at the end, yes? And if you use magnitude 1, you have a new single branching random walk, capital S, which pops up. And that one will be, again, a Brownian motion, and that one is mean 0. It means that it's a standard Brownian motion. Well, it's Brownian motion with the mean 0. So everybody has a positive drift in the branching Brownian motion, but the new random walk, the new Brownian motion that pops up in the magnitude 1 formula, it's driftless. There is no drift.
It depends on how you normalize it.
Oh, I thought that you wanted to put yourself in the situation of star.
Yeah.
So I talk about the star.
I think
yeah.
If you want to put yourself in the situation of
star.
You should rather subtract something from your Brownian motion.
Yeah, that's what I said. That's all your Brownian motion has a positive drift. And I believe the drift is square root of 2, but I'm not sure. Maybe I got you wrong.
This result apparently does not use this normalization.
No, there is no normalization. This is standard branching Brownian motion. So everybody is driftless. That's why you have. That's why you have. Yeah. But I don't think that's a very important point. I mean, it's very elementary. Okay. Thank you.
May I also ask a question? About this relation between KPP and all those processes, variations.
Yeah.
For perturbations of KPP, this is a huge machinery.
Yeah.
Articles.
Yeah.
I'm more familiar not with small perturbations, but say with large perturbations.
Oh, okay. That's even worse, right?
But in any case, the relation is okay. As I understand, there is no formal translation from result for perturbations of KPP to say perturbation of branching in the vault.
In principle, no.
Yeah, but that produces at least heuristic, because actually, at least heuristic translation. Because
Yeah.
up to now, it's also very popular topic in that direction, including stochastic perturbations of KPP. I mean, they introduce this diffusion term, interaction term, and
Yeah. So when I say that there was no known rigorous relationship, it's not exactly the truth. So for the noisy version, you add this noisy version, there is a rigorous relationship leading to a diffusion reaction system, but it's not to the. It doesn't give you back to the branching Brownian motion, unfortunately.
Okay.
It gives you something, but which is not the one you want to.
Yes, no, this I
Yeah. There is a duality saying that, okay, if you add this noisy to
to each KPP, I can construct corresponding branching random walk process, but it's not the branching random walk which you are interested in.
Yeah, it's not the one. Yeah, you want to reach this, let's say, n branching random walk, but unfortunately that's not true. I don't know how to reach that. But I believe for Derrida, that's not a big problem. For him, it's more or less the same. I think that's the difference between physicists and the mathematicians. Mathematicians want to have rigorous arguments. Physicists want to understand what happens, not necessarily with totally rigorous arguments, but what they want to do is to see what happens. As long as they see, then it doesn't matter whether the argument is rigorous or not that's rigorous. That's not a big problem. I think their main interest is to see the connection between this and that. Okay. Well, that's.
We have one more question.
Yes.
So we know from your first lecture that branching Brownian motion gives you, in a sense, a solution to FKPP.
Yes, yes.
If you consider its
Yes, yes.
distribution of its maximum.
Yes, yes.
Now you introduced a modification.
Yes.
Say L BBM.
Yeah, yeah.
Does it solve any perturbed equation or whatever?
Oh, the L one, I don't know. I don't think so. Not as far as I see.
You have no
This, yeah,
no
this is a
connection to
this is a purely
equations.
probabilistic system, and I don't have on the other side of the PDE or even SPDE.
It's
I
a
don't
little
have.
bit surprising because it was introduced by physicists.
Yes.
So
But
physicists should be interested in equations.
Sure. Yes.
Those physicists are a little bit unusual, it's true, but still.
You can ask Derrida in person when he arrives in 2 weeks or slightly more than 2 weeks. And if I understand, he is going to give a talk on this same topic, I guess. So you can blame him for not establishing anything.
Maybe also. We still don't know.
Yeah, I don't know
We
what
still
he
don't
is.
know what he was talking
I don't know. Yeah, the topic of his lecture. But Derrida, I think he's going to talk about this the perturbation of FKPP. Yeah.